All right, we're in our final week here, and congratulations for making it this far. We had quite a few more those first couple days in the other classroom. So, congratulations. In terms of some announcements for this week, the post-test is take it either today or tomorrow. Everything's the same about it. The procedure, everything you'll do is the same as what you did for the pre-test. This is required. You have to do it. I will hold your exam 3 score hostage if you do not take this. So you have to get a score on exam 3. You have to meet this requirement. But in addition, based on your improvements, I'll give you some bonus on exam 3. Okay? So you have to do it, but then try your best. Try to if you improve from the pre-test, I'll give you some bonus on exam 3. Okay, so take it either today or tomorrow. You can enter between 10:30 and 6:30. So be in the door by 6:30. Don't study. No calculator for the post-test. Okay, and then for Thursday, that's exam 3. So we talked about the review outline is posted. Web work is available. So to get bonus points for web work, you have to complete that by Wednesday night at midnight. But it'll still be available for you to study after Wednesday at midnight. And then the answers will be posted then. Okay? Answers will be available. The exam covers about 10 to 15% of it is the Module 6, which was rational functions. And then the rest of it is Module 7, all the trig. And that should be reflected on that review sheet. There's nothing on the exam that isn't represented somewhere in that review sheet. That's a comprehensive bullet point. Web work is a lot of it, but not necessarily. There may be things that we did that aren't in a web work problem. Okay? So the review outline is comprehensive. Web work hits most of it. Questions about your 2 trips to the testing center this week? Yes, ma'am?
I was wondering if after exam 3, are you going to, before we take the final, post what our current grade is?
I can try to do that. I can't promise. But yeah, so I'll try to do that. Because so that current grade, something like end of February, end of March or end of February, I put a current grade up. So the biggest effect to that would be this next exam, right? So if you do really well on exam 3, you can expect that current grade to go up, obviously. Or if you do very poorly, again, down. Okay, other questions? Yes, sir?
The last 2 days or whatever we got left after we take the exam, we're just going to do a review.
No, there's some new material for the final. So like Friday and Monday, there's a few questions on the final that pertain to that new material.
So that final that's in the testing center, we do need to stay between those 2 times, though, correct? The 7 to 9 p.m.
No, that's not in the testing center. This is exam 3, not the final exam.
So what location is the final?
Yeah, I'll let you all know all that. So yeah,
Okay.
so we'll go somewhere else. For the final exam, which is the first day of finals, and we'll meet at 7 p.m. at night on the first day of finals, which is a week from Thursday. I think it's in SCOB. We'll be going to a big classroom. We'll all do it together. Yeah, but I'll give you all those details.
You think it's going to be 7 p.m.?
Yeah.
It's 7 to 9 that day.
7 to 9.
Are they 7 p.m. to 9 hours?
Yeah. So we have exam 3 is this Thursday. Then the final exam, which I haven't given you any details about, is a week from Thursday. It's the first Thursday of finals week. And those details, I'll have those to you this week. Okay. Does it make sense? Other questions? Okay, so I want to give you some heads up about the homework. There's some things I want to mention. The first thing is when you're writing the equations for these graphs, this is one of your homework assignments, homework problems. You're given the graph like we did on Friday, you're trying to write the equation. It's number 65. So just do your best to approximate x and y. So y values should be pretty self-explanatory, but any x values that you're going to need, do your best to just approximate those and use those in your equation. Okay, so for instance, you see this one goes through something a little bit greater than 15. So if you want to call that 16 or 17, that's fine. Whatever. So you may all have slightly different answers for that is what I'm saying. So just do your best to approximate x values based on the graph that you see. Okay? Oh, and then you've got somewhere they give you the equation and they want you to these 73 and 74. So we'll do this today, but and we did this on Friday. This form will not. It's not the form that you want for what we've been doing. So what you need to do is get it in a form like this: a cosine. So this is the form we did: b times theta plus or minus the shift plus the midline. Okay? So what's different about this is our argument. For their argument, they have it multiplied out. The way we analyze these, we had that b value factored out of both those terms. So you'll have to start by changing this argument to make it look like this. A value b times theta plus or minus the shift. Okay, so you'll have to start on 73 and 74 to make it, and then you'll be ready to sketch the graph based on what we said about b and what we said about the shift. But you can't make that b and that the shift. It won't work. You got to have that coefficient of theta kind of factored out. Does it make sense? So I wanted to give you, and then the other thing is you've got this problem about the tide. And so there's something you kind of have to think through here a little bit carefully. It says that at high tide, the shoreline is 20 yards from the stake. And at low tide, the shoreline is 58 yards from the stake. Okay? So that makes sense because when the high tide is when the water's the furthest inland. So it's going to be the shortest distance to a stake on the beach. And low tide is when the water has receded the most, so the distance will be the greatest. So when you're creating your graph, you're going to have maxes and mins. The max is going to be which? High tide or low tide? Okay, so when the max is when the water has receded the most and you have the longest distance from the shoreline to the stake. Do you see? So yeah, so I'm bringing this up because yeah, of course, the top's going to be high tide and the bottom's going to be low tide. No, because we're measuring the distance from a stake on the beach. You see? So when it's high tide, what about that distance? The least. And when it's low tide, greatest. Right? So the top maximum will be low tide. And the bottom of our graph will represent high tide. Because it's the least, because we're graphing, the y-axis is graphing the distance from the edge of the shoreline to the stake. So high tide is when that's least, minimum. Low tide is when that's greatest. Does it make sense? So make sure you have that distinction. Okay, so that's just some notes for your homework, which is due Wednesday and is all pertinent for Thursday's exam. Okay, so let's do that. We had a fan problem that I gave you for Friday. And we never really talked about it. And so this follows up to what we did on Friday, so this is good, some more practice. So this was just a reminder, it says the fan has blades that are 30 centimeters. Okay, and I made a big error here. What I meant here was, this should have been centimeters. So I think what I posted was, anyway, I'll get there. So a fan on the floor span has blades that are 30 centimeters from the center of rotation to the blade tips. When a blade points straight down, the tip is 62 centimeters from the floor. Every 0.4 seconds, the fan makes one rotation counterclockwise. So let's just make a little sketch here. Okay? Not the greatest fan that's ever been drawn. Okay, but basically, the distance from the center to the fan blade is 32 centimeters? No, 30 centimeters. Okay? And then it says when the blade points straight down, that tip is 62 centimeters from the floor. So, of course, to make sense of this, we want to start with a good picture. Okay, so we're 62 centimeters up to that point when it points straight down, and then the radius of the fan, or the distance from that point to the center, is 30. Okay, every 0.4 seconds, the fan makes one full rotation. So one revolution equals 0.4 seconds. So the first thing we want to do is write a function g that outputs the vertical distance of this tip above the floor in centimeters, and that, I think when you did it, it was in feet. That was a mistake. So I had no intention for you to be doing conversions here. It just makes it more confusing. So the intention here was that it would be the vertical distance of the tip above the floor in centimeters as a function of the angle swept counterclockwise from the 3 o'clock position. Okay? So and then we want to sketch the graph. Okay, so we want to take the information here and kind of get the key information and put it together. So what was the first thing we said on Friday to think about in terms of modeling the situation of rotation? What was the first thing we wanted to do? Remember that? He said midline, that's right. So the first thing we want to look at is the midline. So according to this situation, where will the midline be? Where's the midline of the height of the point above the floor? So someone said 92. Do you agree with that? What's that? So where is the midline of this situation? Where should it be? Middle of the fan, right? You want to go with 92? Yeah. All right, so we want 92. So what's the common mistake students make? Midline is at 62. So they say the fan is 62, it's 62 centimeters up to the bottom of the fan, so they want to just add 62. Make sure whatever you add to the function, that's where your midline is going to be. So the midline of this fan is at 92, so we're going to add 92. Okay, what's next? Or what we said next? Amplitude. So amplitude it's from the midline, it's how high up to the max, and also how far down to the min. So what will be that point's height will be the distance up to the max from the midline. Yeah, that'll be our 30, right? And from that, then we can get the max and the min. Okay, so I'll let you figure that out while I graph the midline. So we said the midline's at 92, is that right? Okay, so we'll make that green. So there's the midline. What will our max value be? 122. Min? Okay, the min should make sense. The lowest it's going to get is when that thing is pointed straight down. So that's that value we were given, 62. So we can sketch this channel of the midline and the max and the min. We can draw all those. So 122 and 62. So let's see how awful light blue is here. Can you see it? You see the light blue? Okay. So this is where our function's going to live, right? And when it's at the midline, it's nice, 92 centimeters up. It'll hit as high as 122 and as low as 62. So that function will stay in that range. Okay. So now let's take a look at what we want here. We want the function g that outputs. Vertical distance of the tip above the floor in centimeters for the input of time, as a function of the angle swept counterclockwise. So in general, what function will we write? It's vertical distance above the floor. That's sine. Okay? So what transformations to sine are we going to make so that it gives us the correct graph within this channel? So what's one of them that we'll do? Okay, vertical shift of how much? 62 or 92? So when we add a number, what are we adding? Yeah, no, we're going to add the midline, because remember sine looks like this. So what we're adding is where we want that midline to go to. Because the midline of sine is 0. So we need to get that midline, which is 0, up to where the new midline is, which is not 62 but 92. Does it make sense? And that's a common mistake. The students, they want to add 62 there. But this is going to be the new location of the midline. Okay? Because you're adding or subtracting, where you were before at 0, what you add and subtract is going to be the new location that used to be at 0, which is the midline. Okay, what's going to go into sine? Yeah, because it's just angle because our input of our function is angle. All right, time's not involved here in this number 1. Anything else we need to do? Amplitude. Tell me. How does it change the equation? Right. If it was just sine, then what is it giving us? Just sine gives us what? Radius lengths, as much as 1 and as little as -1. It'll have to be radius lengths. But we want it now in centimeters, up above and below the midline. So we multiply the radius of the length of one radius times the number of radius lengths. And that gives us the value in centimeters. Okay, so let's, before we sketch that, let's see if we can figure it out. So what's the period of G? What's the period of G? So we look at the input, and we're asking what interval of input gives us a full cycle of output. What interval of input will give us a full cycle of output? 2 pi. So 2 pi is about 6.28. What do we do with that 6.28 to help us sketch the one cycle of the wave? Divide into 4, and that should be easy. We know half of that is pi, half of that is pi over 2. There's our pi over 2, there's our pi, Then we have 3 pi over 2 and 2 pi. Okay, sine. Does sine start at the max, the midline, or the min? Midline? So we've done this, and then in 1/4 of the period goes to max, top of the circle, right? So counterclockwise from the 3 o'clock position, midline, max, midline, min, midline. Best sine curve I drew all day. Okay, so let's see if we got it right. $30 sine x plus 92. Okay, any questions on number 1? So
don't understand how you got 92. Like, I know you added 3 and 62, but aren't you supposed to be doing the middle of 30 and 62?
So in this span, what's represented? Where's the midline represented in the fan? The bottom, the top, the middle, right? So and then in just the plain old sine function, where's the midline in the plain old sine function? Yeah, it's 0, right? So I could graph that. So the question is, how much do we want to move this up? How much do we want to move this graph up? So the midline is at 0, right? And where's the midline of this one? How many centimeters above the ground is the midline?
Or 62.
Which is it? 30, 62, or 92?
90.
Do you see why?
Yeah.
Because there's 62 to the bottom, and then 30 up here at the radius. So that's the new midline. The old midline was 0. The new midline's got to be 92, not 62. Yeah, sure. Other questions? Okay, so now the second one is a little tougher. And if we can get the second one, then we're in good shape. Okay, so what's different about the second one? So let's read it. So for the same fan blade tip, starting at the 1 o'clock position, write a function h that outputs vertical distance of the tip above the floor in centimeters for the input of time elapsed since the tip was at the, oh, it should be at the 1 o'clock position. One o'clock position, okay? So sketch the graph with all the key points and details labeled. So it's starting at the 1, so time elapsed since it's at the 1 o'clock position. Okay, so what's the same about this? What are some things that are the same about this situation versus the old one? What's that? Oh, we want vertical distance, so it's also going to be what kind of graph? Sine. Okay, good. What else? Is the midline the same for both these? Which means plus 92. And we want sine. Oops. What else is the same? Amplitude. So we still want 30 sine of something plus 92. What about the input? Time. Okay, so what this whole thing then needs to be represent what? What does that whole argument have to be? So what, if we put something into sine, what does it think it is? Angle. Okay, so the key is that that whole argument is the angle, is an angle, okay? Swept counterclockwise from the 3 o'clock position. But if our input is t, then that angle has to be as an expression of t. So I think what we should do first is just do it without this 1 o'clock thing. Let's do it from the 3 o'clock position first, and then we'll adjust for just for the 1 o'clock position. So we can look at if one revolution is 0.4 seconds, we need to know what angle is swept out in t seconds. If 1 revolution is 0.4 seconds, we need to know what angle is swept out in t seconds. That's what we're saying. All right? So we need to get angle involved here. So how can we get angle involved to this statement right here? 1 revolution equals 0.4 seconds. What's that? Yeah, so really 2 pi radians corresponds to 0.4 seconds. So the question is, how do we get this expression of t? So if you had t and you needed angle, what would you do?
T over 0.4 times 2 pi.
What's that?
Is it T over 0.4 times 2 pi?
T over 0.4 times 2 pi. How did you get that? Oh, so then you plug some times in to see if they gave you the right angles.
Yeah, exactly.
Yeah. Okay. All right. So yeah. Okay. So how can we come up with that though in the first place? So we know that 0.4 seconds corresponds to 2 pi. So really what we're looking for is what multiplier times 0.4 would give us 2 pi. So what number times 0.4 would give us 2 pi? Be 2 pi over 0.4, right? So if you multiplied 0.4 times 2 pi over 0.4, radians, this is radians and seconds. So radians per second. So what should this expression be? So, yeah. 2 pi over 0.4 t. Because this is how many radians per second the fan is turning. So many radians per second the fan is turning. If you multiply that by seconds, you get radians. That's what we want. Okay, so let's take these, oops. Let's get rid of this. Okay, so we need to remember, someone got that written down? I need to erase everything. Someone got that written down? So this isn't really h, this is our initial guess here without the 1 o'clock. So f of t is 30 sine of 2 pi over 0.4 t plus 92, right? So let's just sketch that first and then we'll deal with the 1 o'clock. And that's what we always said. Let's do everything except the horizontal shift and then we'll do the horizontal shift at the end. Okay? So what is our period now? So now our input's in time. So what's our time period that gives us 1 full cycle of output values? That's our 0.4 seconds. So I need to zoom in here. Okay, so there we go. So here is 0.4 seconds. And we want to do what with that? Divide into 4, which is easy. Each one's 0.1, right? 1/10 of a second. Okay, and then sine starts at? Midline goes to? Max, midline, min, midline. So this is everything in number 2 if it were to start at the 3 o'clock position. Okay? So this is for the starting at the 3 o'clock position. So the question is, how do we get it for starting at the 1 o'clock position? So we're going to have the 2 pi over 0.4, and then we need t, and we're going to have our shift plus 92. So the question is, what is the shift here? So how long will it take to do 1/4 cycle? What's the time to do 1/4 cycle there? The angle is 0.pi/2, and the time is 1/10 of a second for 1/4 of the circle. So the question is, how much time is between the 1 o'clock and the 3 o'clock position? So if that's 0.1 seconds, how many seconds between the 1 and the 3 o'clock position? Wouldn't it be 2/3 of that? It would take 2/3 of that amount of time to get there. So we want 2/3 of 1/10. So our fan blade is 2/3 of 1/10 of a second ahead or behind this fan blade? Ahead. So if it's ahead, are we going to add or subtract? If it's ahead, add, right? It's a greater, we're going to add, because it's, remember we talked about this with angles. The angle, if we're ahead in angle, then it's a greater angle you're always adding, right? You're going to add because it's ahead. So it's ahead, so we're going to add 1/10 of 2/3, which is 2/30. So along here, where's the 1 o'clock position? This is the 3 o'clock position. Isn't the 1 o'clock position like 2/3 of the way right there? So now that's going to be our starting value at t equals 0 for our actual function h. So is this going to be a left shift or a right shift? We want this vertical distance, vertical height above the floor, to be at t equals 0. Left shift or right shift? Left. So all these points are going to be shifted over 2/3 of 1/10 of a second. So that one's going to be shifted there. So this one's going to be shifted 2/3 of 1/10 of a second. 2/3 of 1/10 of a second. 2/3, etc. And so if we wanted, we could take this one back, even though there's no negative time, it can just help us sketch. So this fan blade's ahead. It's ahead of the other one. So if you think of time going by, it's going to make its cycle before, right? So if you think of time going by here, it's going to start its cycle before because the blade is ahead. It's going to come at an earlier time, right? If it's ahead, it's going to come at an earlier time. And so you can just take all those key points of your original graph and move them left this much. 2/3 of 1/10. Okay? So let's see if we got it. Do I have it right? 2 pi over 0.4, x plus 2/30 plus, we'll do it red, so it matches. Okay, lots going on there. So we had to talk about lots of different things to get that in the end. Anybody have a question? Did I lose you? If I lost you, can you ask a question? Yes, please.
Do you have to add the shift in seconds? The 2
Um,
and 30? Does it have to be seconds, or can you just put the parentheses around the x and add radians?
Yeah, in this case that'll work. Where that breaks down is if this is another angle, like when we did the bike, when we did the tire valve and the pedal, and this is an angle, then that you really want to make sure that you use the parentheses. But in this case, you're right. So how much of an angle do you want the shift to be? So it'd be, yeah, exactly. So what he's saying is, if we were to multiply this out, we'd have 30 sine. We'd have the 2 pi over 0.4 t plus, if you multiply this out, 2 pi over 0.4 times 2 over 30. So this is pi over 3. If you do the math, you do all that math there, that is pi over 3. So now we're looking at it by angle. So this is the angle rotated in t seconds, and it's ahead by an angle of pi over 3, which is 1 o'clock from 3 o'clock position. That's our pi over 3. That's what you're saying, right? So that works in this case. But again, if t is a different angle, and you're transforming one angle to another angle, this gets a little dicey. And so I would just stick with this whenever that input is at an angle. Yeah. But here it works nice. Other questions? Yes?
Could you have, like, is there multiple ways of doing this? Can you
Yeah,
do
there's.
a graph that you have, it's just written differently?
So tell me more. Like, did you?
Kind of more along the lines of what he did, like simplify 2 pi over 4 pi to 2 pi.
Okay.
And then instead of doing the 2 over 30, I did, remember that quiz that we did? I did the sign for that, where you put in, it said plus grad 3 over 2.
I'd have to look. I'm not sure because rad 3 over 2 is an output of sine. So you're putting rad 3 over 2 in here.
Right, because it's the angle of the sign that you need.
I'd have to look at it. So rad 3 over 2 is a value of sine. It's an output of sine. So it wouldn't make sense to put it inside. But I'd have to look at exactly what you're doing. Okay. Other questions? All right. So there's a. We want to look at the topic of inverse sine, and we'll start it today, and we'll finish it up Wednesday. But as we're talking about inverse sine, it's lots of good review of exam 3 stuff, building up to it. So, can I erase? Any more questions on this? Okay, so here's a warm-up task here. So f, the function f here is defined as sine of theta, and g is defined as cosine theta. So this is good review. To really understand that means understanding the input and output of each of those. So explain in detail the meanings of the input and output of each function. You're going to do this with a partner. And then number 2 is referencing the function f, which is the function f from number 1 at the beginning. Okay, so this f refers to the way f is defined up there. So you're going to interpret each expression and find the value without a calculator. So this is all good review, all stuff you need to know for your for exam 3. Good review, and then it's also building up to the next topic. Okay, so find a partner and talk through this. Go. So we really struggled with this in the first class, okay? But at the same time, we said it over and over again in the last month. So you've got to know this. You've got to know in detail what the meanings of those quantities are. So, okay, so okay, half of you should be talking. Okay, right here in the white t-shirt. Yeah, yes you. Tell me what the input of F is.
So it'd be the vertical distance from horizontal.
Kind of lost, okay? How about behind him in the red tie? What's the input of the F function? Okay, what is it? Okay, is that enough detail? Angle and radians. What do we think?
Angle in anything.
Angle in anything. Any angle?
Well, as long as it's the angle theta. It's an angle measurement.
An angle measurement. Go ahead. So what's the input into? That's okay. All right. So do we agree that it's an angle? What angle is it? Swept counterclockwise from the 3 o'clock position. If it's not that angle, then it's not sine. Okay? It's not. Sine is dependent on or thinks that what's coming into it is the angle swept counterclockwise from 3 o'clock.
Unless you have a shift, right?
No, but the argument will still be, so we'll shift it, but the argument then becomes like theta.
Well, I'm saying, like, how did we do the previous problem at the 1 o'clock position, but it was still sine?
Yeah, because we had a shift. We had a shift of the input, but this represents, in this function, it represents whatever the argument into sine is. Whatever sine function we have, it has an argument, and that argument has to be the angle swept counterclockwise from 3 o'clock. Does that make sense? What's that? Are you looking at this? Well, no, so you can take on many angles. So it's a varying quantity. Does that answer your question?
Yeah, sorry, I thought we were just talking specifically about that.
No, I'm talking about number one. What's the input and output of the sine function? Just what's the input and output of sine? Okay, what's the output? So, how about in the gray shirt back there? Yeah. Vertical distance above the horizontal axis and radius lengths. Perfect. Well done. Vertical distance above horizontal diameter in radius lengths. We have to have this down pat if we're going to understand anything else. Good. Okay? So now, what does that expression represent? F of pi over 2. What does that mean? He said, given that angle, what's the vertical distance above the horizontal diameter? Agree? Yep. And so what is that? What does that answer? 1. Okay, what about pi over 3? Where's pi over 3? Tell me where to stop. How many radius lengths are we above the vertical diameter at pi over 3? This is our unit circle stuff, right? Radical 3 over 2. 7 pi over 6. Where do I stop? Oh, okay, most of you got it. All right, right there. Value is negative 1/2. Right, at 7 pi over 6 is right there. 7 pi over 4. Tell me when to stop. Here? Here? Halfway. Value is? Negative radical 2 over 2. 2 pi over 3. Uh-oh. Start again. 2 pi over 3. Right there. What's that? Radical 3 over 2, right? Okay, so that's a little review. But this is, in terms of, now we want to talk about what's called the inverse sine function, or arc sine. That little -1 should be up higher here. So F inverse x. All right, so this is called the inverse sine or the arc sine function. Arc sine or inverse sine, same thing. So what are the input and output of the inverse sine function? Tell the person next to you. Go. What's the input of inverse sine? What's the output of inverse sine? Go. Okay, yellow shirt. Tell me. Okay. Good. And then what will the output be? Someone else. Black shirt in the very back. Good. So that seems easy enough, but we run into difficulty here really quickly. So we got to know that. We got to have that down. The inverse sine will have the input and output will be switched. Now your input is vertical distance, and your output is angle swept counterclockwise. Okay, so you imagine now your input is how high above or below the vertical horizontal diameter you are. So for instance, if we put -1 into the arc sine function, what are we going to get? So what does that -1 represent? Yeah, that would be down here at -1, and the output will be? Okay, will it be 3 pi over 2? Well, that certainly is an angle that gives us that vertical distance. What about 1.3? How about that? So we're asking what angle gives us a vertical distance above the horizontal diameter of 1.3 radius lengths? What's that? Should make you uncomfortable. Not possible. Why? Because what's the maximum vertical distance we could have? 1 radius length. So this is not possible. So there's a restriction on the domain. The domain has to be between -1 and 1, because that's the lowest and highest value of, in radius lengths, of vertical distance above horizontal diameter. Okay, and we'll pick it up there Wednesday. You got written homework. Don't forget the stuff I told you at the beginning.